This is video 16, which is the fifth video in our mini-series exploring serial communication between STM32 MicroPython and a desktop Python application. The code for this video is at the GitHub site. The information presented in these videos on MicroPython should work as well on any STM32 F4 board. All code examples have pin definitions at the beginning of the file to allow the programmer to alter as needed. As this channel covers multiple microcontroller solutions over time, please subscribe to stay informed and click like, as that really helps. In this video, we continue to explore serial transfers by looking at Python packages with all of the functions we discussed to date. Using packaged Python class libraries may allow us to use best practices in our projects. Through internet searches, we located two packages written for Python on the desktop and that interface to microcontrollers. Each package uses pySerial on the desktop to communicate. Unfortunately, for now, they just support Arduino. Can we use these with MicroPython? Here's a quick review of what we learned in the past videos. The communication should provide framing, error detection, and serialization. We also ideally would like an identifier and ability of the program to handle acknowledgments. In this manner, we can perform reliable data transfers. In this video, we will focus on the first package, pySerialTransfer. The nice thing about this package is that one can pip install the software. And additionally, the Arduino is also capable of being installed through the managed libraries capability of the Arduino IDE. However, for the purposes of demonstrating all the features, I'm going to be using the zipped version, which I've unzipped, and we're going to look at in Visual Studio Code. Okay, I have the software placed on a directory, and it consists of the pySerialTransfer class library and two example test programs. Well, additionally, there's a CRC file as well. So let's run this program, and then we'll come back and look at it. And we're going to run it in loopback. Okay, I've set the program up to listen for keystrokes on the keyboard. So the letter S will send the data structure, and the letter Q will quit the program. So let's press S. Okay, you can see that we've sent out a string. Well, what is this string? Well, in the past video, we used 15, 1 for the value for true, 1.414 is a floating point number, and a string hello. So in this program, the first thing we've learned is that it organizes its data into structures. So the program has packed that structure into a frame, and it's sent it, and we've turned it around and received it via this link available function, which we'll look at in a little bit. And it has read it and parsed it out, and as you can see, it's resulted in the values 15, 1, 1.414, and an approximation that floating points do, and the string hello. So we can see the program works. All right, let's go take a look at the code. As I mentioned before, the first thing we see is the structure. I added item AA to the test file, so the original test data file had almost the same data that I had. I was very surprised, and I added this AA to represent our Boolean true or 1. But as you recall, MicroPython cannot handle Boolean in structures at the moment, and so we have to send it as an integer. So I've changed it to a 1, as you can see here. Let's scroll down to where we send the data. So the authors of the program use this clever way to build their payload. So each object is put through this tx underscore object function, which builds that object into the message that it's going to send. So you can see each of the three objects, well, four objects have been put into the tx underscore object function, and then it uses the send function to send it. And interestingly, they pass just the size of the function to the program. And we'll see the reason for that is because they're putting this string into a buffer that's 250 characters wide. And by sending the size, they know only to send, in this case, 23 bytes to the microcontroller. All right, so now let's look at the class library code to see how the communication is achieved. All right, the great thing here is that pySerialTransfer puts all of its functionality into one file. First, let's go to the declarations. And when we do, we see that the start byte and the end byte is being declared. So that indicates to me that they're not using COBS, they're using some form of HDLC framing. Okay. Next, you'll see a lot of variables set up for the structure formatting, as we would have expected. And you'll see a definition of state, so that indicates that they're going to be using a finite state machine. Let's go down to the send function and look at it. All right, it's way down here. Here we go. Oh, and the authors of this class library did a really good job of putting in comments that throughout the program. So each function is well documented as far as how it works and what it does and what parameters it uses. So we can see that to do the send, we're building a message, and we start with something called overhead. Then we stuff the package, we calculate a checksum, we append a start byte, we append a packet ID. So that's new. We've not seen that before. So here, this class library is actually using a packet identifier. Then they have this object called overhead byte, which we need to learn more about. They send the message length. That's good. They read each byte out of the payload and append that to our buffer. They add the checksum that they calculated up above, and finally they put a stop byte. So that really tells me that we're doing an HDLC type frame, but we'll see more about that in a minute. Okay, let's go back to the beginning here. What the heck is this overhead byte that they're calculating? All right, let's see if we can find that. So we'll select it and go to the definition. And we see a statement here in their comments that they're creating a COBS overhead byte. So that confused me because they're pretty much using HDLC type framing start and stop bytes. But they clearly say that they're using COBS here. So let's look at this. Let's bring up our COBS form. So I brought up on the screen a screenshot that we did a couple videos ago about COBS. And here we see in COBS that it describes how one performs overhead byte stuffing with COBS. And you can see here that it's talking about the 0 data byte, but that the 0 data byte will not appear inside a COBS string. What it does is it replaces the 0 with its overhead byte, which is really a position indicator as to where a 0 might appear in your payload. And then that's a reference to the next 0 in the payload. And only do we see zeros at the end of a COBS frame and at the beginning. So when we look at this overhead byte, it's not doing that. Here you can see it's using start byte. And further, if we look, it's using this stuff package routine here. And this stuff package does not do what we think. In fact, if we come down here to the print statements that I did, and we look at the message that we're sending, you'll see lots of zeros. There's zeros in here for the number 15 and for the number 1. And what are those doing here? They should not be here. And the message, it's kind of like a reverse COBS, as they put a 0 where the start byte would reside. And I consider it some form of hybrid HDLC byte stuffing mechanism that they call COBS. But it turns out if both the sender and destination are using the same hybrid code, then the transfer works, as we saw. All right, let's go back to the send function and see what else it's doing. All right, the next thing is we've got the start byte, we've got the identifier with the overhead byte that we just talked about, the message length, and we're placing the message itself, the payload. And the next thing we come to is this found checksum. So let's go take a look and see how that's being created. So found checksum is running this CRC calculate function, and that is in this file CRC. And when we come and look at this code, the first thing we see is in this initialization a CRC underscore length of 8, which indicates to me 8 bits. And so what does that mean? And when I come back and look at this, I realized that it's only appending a single byte here. So what are they doing? Well, they've got this fancy algorithm that's calculating a CRC 16, and then they're using some mechanism of just getting 8 bits of that and using those 8 bits as their checksum in their program. All right, so that's different. And the next thing, the last thing is the stop byte. So that's pretty straightforward. So now let's look at the receive function. So as we recall from our TX data, it has this link available. So we need to go find that function in our pySerialTransform. Unfortunately for me, it's just below the send. All right, this consists of a serial style available function. And it uses a finite state machine like we used in video 13b. First thing they do is they find the start byte. And once they do, they set the state for the next step that they have to do, which is find the ID byte. The ID byte right here, okay? What we do is we're going to just throw that away because this program doesn't use it any further. The next thing we do is find the overhead byte, okay? So the overhead byte can be different. When we run that function, the default is to put in the value of 0xFF. Then it will replace that with this overhead byte, and in other words, a position into the payload will be put here. All right, the next thing it does is find the payload length, which is a single byte. So that tells us that their packets are going to be no larger than what you can do with 255 characters. They take that value, they get that value, and they save it. Okay, so and they set the state to payload. So let's go down to the payload section. They're just reading in every single byte until they get to the length of the payload. When they're done, the next thing they do is find the CRC. Okay. In this step of the finite state machine, they're going to go calculate a checksum based on the buffer that they've received so far, and they're going to save that, and then they're going to compare it to the byte that they found. Okay. So this is similar to what we've done in other programs. We have a byte that we calculate, and we have a byte that we found in the string. And if it's okay, they move on to the next step. If not, they produce an error and exit out of the packet. In this case, we assume that they found it and that it's okay, and so they move on to the next step. And the next step is to find the end byte. So here, when they find the end byte, they're ready to stop. Okay. They unpack the packet, and they read. They set they read that many characters that they saved up above. So let's take a look at this unpack packet and see what it's doing. All right, it unpacks all the so-called COBS, stuffed bytes within the array. Okay, and when we look at this functionality, we will see that it's very similar to the routine that we looked at above that did the byte stuffing. So it's looking for all those positions. It starts with that overhead byte, right? And it starts indexing its way through the buffer, and it replaces that overhead byte with the start byte. All right, other than that, let's go back. Once they've unpacked the buffer, then they can pass on the message. So let's go back to our program, TX-transfer. So we're basically at this point. So this link available did all those things. And so now, if we have bytes to read, okay, I added this. So I wanted to see for sure that it was getting the data. So I've created this empty structure, and as we go through, we're going to populate this empty structure. So first I printed out that it's empty, as you can see down here, and then we're going to fill it in. And how do we do that? Well, it's got this clever way using the rx_object function within the library to take the object type and use that to extract that size object out of the buffer. So as we recall from our last discussion on structures, structures have this format defined by these characters that represents the size of each of the values that it puts into the byte array. So in this case, since we were saying the very first object is an I, or an integer, it's going to extract out an integer and put it into this Z. Makes sense, as we've got the value of 15 that we're trying to parse out of that string. The next item is the 1, so we know that's an integer, and so we extract that out. And the next item is that floating point number. So we use F to extract out of the received buffer the floating point number and put that into Y. And finally, we use this routine to extract 5 string characters and put them into the variable R array. And as it's doing this, it's building up this record size, so we know exactly what the size is of this data. And then I edit this print statement, so you can see down here that we received a 15, a 1, a 1.414, and the string hello. And so what do we need to do to make this work for STM32? So on STM32, I had hoped to use a lot of the code that we had already created to build our program. But as you can see from my discussion on how it does the framing, how it does the CRC, and how it does the schema, all those things are unique to this program. So what I did is I simply copied all these functions from over here in Python into a MicroPython file. I didn't put it into a class, although I could have. But all these functions are very, very much the same as the functions in the Python, but they're using they're written for MicroPython. So let's run this program against the Python desktop application, and in order to do that, we have to take our app out of loopback. So let's come here, and you'll have all these files available to you through the GitHub, but when you get them, I will have them start off in loopback so that you can play with it. First thing we do is in the initialization. That's the best place to change it to loopback. And in the example data program, we also want to change it at the top. So there's a COM port setting here. So we're going to change it to use the COM port of the Bluetooth serial port on my desktop. So now I'm going to plug in the serial, the UART serial module into the STM32. In the library, there's this section of code that is used to identify the serial ports, which we don't need in loopback, but we do need all this when we run the program. All right, so let's go back to our Thony, make sure it's running. It is. And we'll restart the program here. And for some reason it still thinks I'm in loopback. Oh, because we didn't save the program. Very good. Okay, so Python is now connected. The Python on the desktop application is now connected to the Thony. So if I press, let's move this over here. If I press S on the keyboard, you can see that the data shows up on our STM32, and it has received that message with that long 23 bytes. Okay, it's got the 23 bytes in here. It's unpacked it. It's got the buffer, and it's read the payload. And look, here's the 15.1, 1.414, and the word hello. Okay, that's great. Let's send from the STM32 to the desktop app, and we do that by pressing a button on the microcontroller. Okay, we pressed a button on the microcontroller, which has formulated the message, which in this case is the same as what we had, and we've pushed it to the desktop. And the desktop has received it as before, as 15.1, this floating point number with the slightly approximation that floating point numbers do, and we've got the string hello, no problem. Okay, that's great. All right, so I'm going to leave these print statements into the code so that when you play with this and extract it from my GitHub site, you'll be able to try little experiments like this where you can make changes. In summary, we ran the serial transfer program in loopback and then with the STM32. When we reviewed the class library code, we observed that the class had 4 communication functions as we expected. We were able to easily migrate the Python code to the MicroPython and connect it to our microcontroller. Can we use this class library? Well, I made a chart of cons and pros. For the cons, for serialization, we need the identical schema in both systems. As you can see here, I had to have the schema on the microcontroller and I had to have a schema on the desktop. So, but the benefit of that is you get, as you recall from our last video, you get the tightest, smallest byte string. The next thing is the CRC calculation. It's just a byte. Now, is that sufficient? So it gets down to your project. You know, can your project function? Okay, the last item was the byte stuffing. The byte stuffing, really, I think you need to have your project perform your own test and see if it works with the data that you intend to transfer back and forth. On the pro side, the example message transfer is fast. In fact, all serial transfers that we've been doing throughout this whole series are fast. I have a screen. So I connected the logic analyzer to the transmit and receive pins on the microcontroller to see what it was doing. And you can see here the serial communication bytes, and it's the 23 characters, right? And how quickly did it do this? Well, I'm running the UART at a baud rate of 38,400, and it was able to perform that send function in 6 milliseconds, which is very fast. If you press a push button, you generally will debounce it for 50 milliseconds, and this transfer occurred in 6 milliseconds. But wait, I'm running this really slow. You could run this at a more reasonable rate of 115,200, which is 3x this. And as it turns out, I did that test as well. And so this is the same test running the Bluetooth connection at 115,200. And you can see that it performs, well, as we expected, 3 times faster because it's 3 times the speed. And so it completed that transfer of 23 bytes in 2 milliseconds. So that's very fast. So you would have no problems sending really large transfers and receiving them on the desktop well within the 1 second timeout that we were using in our last video. On the logistics side, the software can be installed with pip, and it already has a supported library for Arduino. So I think your project has an interesting choice here. It should consider this package if the trade-offs that we discussed are suitable for your project. In the next video, we will continue to explore serial transfer technology further. Thank you.